Any general questions, problems, anything? Okay, so we were talking salts, and again, essentially the salt is nothing new, right? In two ways. One, I've been harping a little bit, and I will continue to harp on the idea that if you have a salt dissolved in water, the first thing you do with it is dissociate it before anything else, right? And once I do that, I have actually an acid, the cation portion, and a base, the anion portion. So throwing a salt in the mix really is just throwing an acid and a base into the mix, right? And so again, my separate into ions is generic, whether it's an acid base problem or not, right? This is going to be a constant theme from this point forward. If I have a salt and it's dissolved in water, I dissociate it. One, because it does, right? And two, because again, typically, if you are careful in your choice of chemicals, it's only half the achievement, whatever, right? Very rarely does the salt contain two things you need, right? It's just that ionic compounds always come as a matched pair in the solid form, and so you can't help but have something along for the ride, right? And so, right, if it's a salt and it's dissolved in water, it dissociates, right? The cation is always the conjugate acid of something, and the anion is always the conjugate base of something, right? To figure out what the something is, right, for the cation, you really have two choices, right? And again, because my metal ions are technically conjugate acids but don't have protons, the cations are probably the more confusing thing. If it happens to have a proton, I just take it off. That tells me what the conjugate base was. If it doesn't have a proton, right, and so again, we're talking, metal ions here, right? If it's a sodium or it's an iron or it's a whatever, right? I put as many hydroxides on as it takes to balance the charge, right? It is, the cation is technically the conjugate acid of a hydroxide, even if it doesn't itself have a proton, right? The anion is easier. The anion just is always picking up protons to find out what its conjugate acid was. And again, I add as many protons as it takes to make it neutral, right? And then again, if I've rationally chosen my salt in this problem, right, hopefully half of it, at least half, right, will not be participating in the acid-base chemistry. It's a spectator, right? And the ones that make spectators are the things that are conjugates of something strong, right? And so if my acid or base is strong, the K is effectively near infinite, which means the K of the conjugate is effectively zero, right? And so, right, sodium chloride, there's the salt, table salt, right? Again, if it's dissolved in water, which this is because it's a solution, 0.1 molar, right? First thing I do before anything else is separate it into ions, which means I don't really have sodium chloride. I have sodium and chloride ions, which are separate. And again, technically, sodium ion is an acid, even though it has no proton because it's in water. Chloride is a base, right? again, for the cation, I'm either going to add hydroxide or remove a proton if I have one. Since it's sodium and it doesn't have a proton, I'm going to add as many hydroxides as it takes to be charge neutral, which in this case is just 1. And so again, sodium ion is the conjugate acid of sodium hydroxide. And for the anion, I'm just going to add the H pluses back, as many as it takes to be charge neutral. In the case of chloride, that's 1. And so chloride is the conjugate base of hydrochloric acid, right? And now it's really just a question of Ks, right? And again, these are what I have, right? But these are what I look up, because again, the tables tend to only show the dominant compound in the conjugate acid-base pair. And so, you know, the question is sodium hydroxide, what's the K? HCl, what's the K? Right. In the case of both of these, right, they're strong, which makes the K near infinite. Right. Again, those are the compounds I have to look up. Those are not the compounds I have. I have the conjugates, right? And so technically, right, what I want ultimately is the K of the conjugate. But again, if this is strong, the Ks are essentially infinite, right? So if I calculate the K of the conjugate, they're effectively 0. Right, and so sodium chloride is in fact a neutral salt because both the acid and the base that I get from dissociating the sodium chloride are the conjugate of strong acids and bases. And so they themselves have no acid-base role to play. Right. And so the sodium chloride should be really pretty much pH 7. Yes, no? And again, the situation is different for ammonium chloride, although my process is the same. Right? Ammonium chloride is ionic. It's a polyatomic with a nonmetal. So I've got a salt. It's in solution. First thing I do is separate it into ions. That gives me ammonium and chloride. Right? And so the cation ammonium is an acid. The chloride, just like a minute ago, is still a base, right? And so it's really, again, just a question of K, right? And again, the thing I have, I usually cannot look up because it's a conjugate. So for the cation, in this case, ammonium does have an H plus I can take off. And so I do. And so, as you probably know by now, ammonium is the conjugate acid of ammonia. Right. And for the anion, I just add H pluses. And so like a moment ago, chloride still the conjugate base of HCl. Right. And so again, there's a distinction between what I actually have and what I'm going to look up. Right. HCl still a strong acid. Ammonia, on the other hand, is a weak base. Right. So again, since I have chloride, right, as the conjugate of something strong, right, the Ka of this is approximately infinite. The Kb of Cl minus, therefore, is approximately 0. So I can ignore the chloride. On the other hand, good old ammonium is not a great acid, but it is an acid. Right. And so the ammonium chloride solution should be acidic. Right. Assuming, again, it's only ammonium chloride, there's nothing else in there. Yes, no, maybe. I mean, the rest of it is just your standard 3-step equilibrium problem approach, right? I now have a solution of ammonium. So balanced equation, ice chart. Solve for X. Right. You know, in this case, the assumption probably works, so it's always worth trying anyway. Which is, something like 7.5 times 10 to the minus 6. All right, and so my pH is the negative log of 7.5 times 10 to the minus 6. All right. Even if it's just a salt solution, depending on what the specific ions are in the salt, right, I could be acidic, basic, or neutral. Right. And again, in practice, if I'm rational in my choice of salt, I have probably chosen it, right, so that half of the salt is a spectator, right? So, you know, if I were trying to, we were talking buffers not so long ago, if I'm trying to make acetic acid acetate buffer, right, in theory, right, any acetate salt will make a buffer, right? But again, if I'm being rational about it, you know, I'm going to pick something like sodium acetate or potassium acetate, or even, dare I say, magnesium acetate. I'm not going to pick iron acetate. And the reason is not that I could not get acetate from iron acetate. The reason is that I do have a conjugate acid in the iron acetate molecule that is going to have its own acid-base chemistry going on, right? All three of these cations, right, come from strong bases, right? So my rational choice has intentionally chosen the cation to be a spectator, right? And again, of secondary concern, but important nonetheless, sodium and potassium salts in particular also tend to be very soluble, right? Iron acetate may be a little soluble, but it's nowhere near as soluble as sodium and potassium. So if I'm trying to get acetate into solution, helps to have something that's soluble, right? But I also have the added benefit that the sodium potassium are spectators. In the case of iron, right, I probably have limited solubility, right? But the bigger problem is that iron hydroxide is a weak base, right? Therefore, this is an acid. So it will not be strictly a spectator. And so it's going to have its own acid-base chemistry, which is going to potentially shift the pH of the solution I'm trying to make. All right. Now, it might not be a big factor, depending on what specifically the Ks are, right? The acetic acid might still dominate, right? But why take the chance, right? Why even insert the added complexity of having a less soluble acetate salt that also has acid properties when, again, I'm allowed to decide what goes in my beaker. I can rationally choose to use something like sodium or potassium acetate that is going to have a really high solubility. And again, the added benefit that the sodium and the potassium do nothing. All right. Yes, no, maybe. Zoom people, yes, no, maybe. Dead silent on the Zoom. They've all passed away. All right. And I don't know, maybe Monday we'll do what I like to think of as acid-base soup, right? I can have multiple acids and bases in the mixture. Right? I can have as many as I want. Ultimately, again, all of the acids have to reach their equilibria. All of the bases have to reach their equilibria, both separately and together, right? But I let the Ks sort them out. I was going to sort of set one up now, but since there's been a lot of questions about finding information on the project, I do want to discuss searching right now. I did recommend, and this remains true, that you use Google Scholar to search for technical information, because it does filter out sort of the popular press news that might be associated with your compound, especially, you know, if you have something that's in the news, right, or something that's of common interest like solar energy cells, right, batteries, right. You can get a lot of sources that aren't technically reliable and also are getting in the way and burying the technical sources. Google Scholar, on the other hand, will only show you technical sources. Now, that said, especially if it's a reaction that you're not terribly familiar with, using Google regular, right, as the source or as the search engine will give you, you know, basic information around the topic. So I would use, you know, some version of both, right? But you also have the ability to do more advanced searching. Now, some of that could be by, right, what you actually put in here. I hate to do any particular reaction, but I could. I mean, if I just type in photosynthesis, I'm going to get hundreds of thousands of hits, right? Actually, 601 million results. You know, please spend some time sorting through all of them, right? Now, I do get what could be useful to me, right, if it's a reaction I'm not familiar with, which is it's got definitions of the word. It's also going to have right up front things like the Wikipedia entry. Britannica appears to be the second one, right? You will also come across, for something like that, what are the undergraduate, you know, discussions of the science of photosynthesis, right? That is useful information, especially if you're not terribly familiar with the reaction you chose, right? It may not have any of the more specific kinetic information you're currently looking for, right? Which is where Google Scholar would come in, right? If I do the same thing on Google Scholar, right, I'm still going to get a ton of hits, right? But again, since it's only looking at literature, scientific literature, I only have 1.5 million hits, right? But they're going to be on all aspects of photosynthesis, right? Not strictly chemical, and certainly not strictly kinetic, right? I can start narrowing it down, of course, if I start searching for something more specific, right? I'm down to 389,000 hits. And if I did the same thing with good old regular Google, again, I probably have a lot of popular science in the way. That's not that unusual a term, right? But at least I went from 600 million results to 5 million results, right? Of course, I'm going to get a similar, but probably slightly different set of results if I use rate of reaction or similar kinetic terms, right? And so one of the challenges, depending on what sort of subdiscipline your reaction falls into, is really what words to use, right? For example, if you're talking about enzymes, right, it is very common in biochemistry with enzymes to talk about turnover, right? That is essentially a rate, right? It's the number of molecules per second or minute or year that's binding to the enzyme, right? We don't tend to use the word turnover to discuss orders of reactions for the kind of bimolecular small molecule stuff we talk about in class. And so there can be a slight language difference, right, based on whatever subdiscipline you fall into. And so it could help, right, to search around different versions of kinetics, right? And so there are rates and there are rate constants, there's temperature dependencies and there's concentration dependencies, and feel free to use any or all of those terms, right? You also have the option within Google to do somewhat more advanced searching, right? If you go down to settings here, it might be different on a Mac, I don't know. Right, you have an advanced search function. There's a similar, we'll look at in a second, advanced search function in Google Scholar, right? That allows you to really hone in or expand your search depending on which version you use, right? So if I'm looking for all of these words, right, if I throw in, I don't know, oh, look, there's a whole bunch of them. Whoops, when I was playing around earlier, right? Now it's only going to show me results that have all three of those phrases in there. The quotation marks mean it's looking exactly for activation energy. If I take the quotations off, it'll give me either activation or energy, right? But now if I've got an article about photosynthesis that doesn't use the term Arrhenius, it won't show to me, or it'll at least bury it in the list. Right. If I were, this exact word or phrase is more useful if I've got a quote or something I'm looking for, right? Where then it's looking for the exact sequence of words, right? And so, you know, right? If I put photosynthetic pathway in there, it'll only give me results that specifically say photosynthetic pathway, right? Whereas if I put it up here, right, it'll give me things that say photosynthetic and pathway, but they don't have to be exactly next to each other as a single phrase, right? Whereas if I put photosynthetic pathway down here, it'll give me everything that has either photosynthetic or pathway or both, right? And so it won't need to have both, right? And so I can change the way I search for it. This is useful again in either narrowing down the search or expanding it, right? And you can do the same thing with Google Scholar. It's over here on Google Scholar for some reason. Both Google, different place, and I'm sure whatever your favorite search engine is has a similar advanced search function, which allows me to change the way I structure the search, right? And so at least one of these words, right, if I type the same phrase in here, it's looking for either one, not both. I can also exclude words. I'm not sure how helpful that is or isn't here. I mean, it's helpful if you tend to have, you know, something that's popping up and getting in the way because it's so common to the discipline, but not what you're interested in, right? Many people have found an article, right, which doesn't necessarily give them all of the information they have, but seems to be in the area, right? For like, I had several combustion people that had an article on modeling the kinetics of combustion. Somebody sent me a paper yesterday on modeling the kinetics of RNA. And I said, if there's a model, there must be numbers, right? Because it wouldn't make a lot of sense to construct a quantitative model that predicts a rate that nobody measured, right? That doesn't mean they necessarily reference it in the same article. On the other hand, right, I can find other articles by the same people, right? Or if I go to Web of Science, I can even do a citation search to see who has cited the article I have, right? Which may allow me to find the related, more specific information I want, right? A lot of sort of information searching really is more about finding a foothold in the field, because then you can build from there. If you can find the seminal paper in a field, right, everybody's going to reference it. And so just from the citation, right, you can find hundreds of related articles that will have hundreds of related pieces of information, right? And, you know, people tend to work in the same field, right? And so, you know, if Smith and Jones published a paper in 1988 about photosynthesis, they probably published papers in the 20 or 30 years since then until they retired or died. In which case, again, searching for articles by the same people will give you added information. Right. The other nice feature here, right, is I can just look in the title. Again, that's more helpful if I have some idea of what I'm looking for, or I can look for the words anywhere in the text of the article. Right. You know, for your specific needs, right, a lot of it depends on what discipline you're in and how familiar you are with the lingo in that discipline, right? A lot of the biochemical ones have very different lingo. Now, if you chose the biochemical one because you saw it in biology, you know some of the lingo, right? Because the biology lingo, the molecular biology lingo is very similar to the biochemistry lingo. They're overlapping fields, right? If you randomly pulled a topic off a list or it's something you just heard about, maybe you don't speak the language, which again is where I would use regular Google sort of as a means of getting background information, especially for things that are likely to pop up in an undergraduate course, right? Photosynthesis is in, Gen Bio, pops up in some chemistry courses, right? There's going to be educational materials on photosynthesis. You won't find those in Google Scholar, which again is searching in the literature. You will find them in regular Google, right? And so, ultimately, project 3 is going to be thermodynamics, and energy issues. So, there's other stuff to find later. At this point, since the concentration's on kinetics, right, you're looking for kinetics, but you may have to speak the language a little bit. Even the naming of things, right? If a reaction has a specific name, right, you're going to get much more meaningful results if you're just searching the name of that reaction. Right. Questions on that? Anything?
Yeah, I have a question, Professor.
Yes.
So, back to the sources, how you said that getting basic information would be better to use Google itself. That's not going to affect our grade for the quality of the sources, right? Well, I mean, I wasn't going to obviously base
No,
everything off
I hear
that.
you. I just, if you address the relevant issues in the paper, the grade will take care of itself.
Yeah,
I worry about, this is why I hate rubrics, right? The question was, if you use regular Google, will that affect the quality of the sources and therefore the grade, right? If you get all great sources, you can check the box for sources on the grade. On the other hand, if you didn't use them or synthesize them properly, that's where you start to get a paper that seems to check all the boxes but is unreadable. So I would not get hung up on point deductions here or there. But again, I mean, there are reliable sources. It's not that, how do I want to put this? It's not that I'm necessarily saying my Google Scholar results are more reliable than everything that's on regular Google. These papers, many of them will pop up on Google. The problem is they get buried, right, by, the more pop science stuff and whatever, because of the way they do the search. I mean, I'll take this article title and put it in regular Google, it'll find it, right? It's on there, but right. But I mean, this is an ACS publication, right? PubMed is medical publisher, right? These are all perfectly legitimate scholarly articles that Google, not Scholar, found, right? The problem is, right, if I am searching generically in here, right, as opposed to specifically, right, I'm going to get all of those pop science stuff that's going to just bury the technical article. In theory, you could find everything you need using regular Google, right? The only reason I suggested going to Google Scholar was to filter out some of the stuff that's going to get in the way. I mean, especially you take something like photosynthesis, you're going to find, grade school level stuff talking about photosynthesis that's going to be peppered in there with, whatever you're looking for, right? We had 600 million results, right, on that first search, right? Because it's so common, right? Now, if you have a reaction that's less common, you'll have less of a problem using regular Google as opposed to Google Scholar, because there won't be a lot of Newsweek or Time Magazine articles, you know, mixed in. If you've got a fairly advanced reaction that doesn't tend to get covered in high school chemistry or biology or even undergraduate chemistry or biology, there'll be a lot less of those um, websites or web pages mixed in, right? I mean, something like photosynthesis, I mean, a lot of your results, if you start going through it, are probably, you know, answer keys and homework problems, you know, from various colleges or publishers that are also in the mix because, you know, I mean, I forget what somebody in office hours had popped in. And so my tendency is to throw something in a search engine and see what I see as opposed to what they're seeing. And I was looking for the activation energy or something, and it popped up in somebody's test. Of course, not knowing whether, you know, the test did not cite the source of the number, so I don't know how reliable it was. But I think it was MIT. Somebody had posted the answer key to their biochemistry test that had the activation energy for the reaction in it, allegedly. Because again, I don't know the source of it. Right. And so all of that stuff is mixed in regular Google. It's not that you can't get regular Google to give you specifically what you want, especially if you start searching for something very, very specific, right? In this case, I'm down to 940 results because I gave it something that's so specific, right? On the other hand, you know, if you make it really, really specific too soon and are not 100% fluent in the field, which generally speaking, we're not going to be, right? I'm also possibly filtering out the information I want, right? So it's not about which search engine found it. Ultimately, it's about how reliable the reference is, right? And so if your reference ends up being a 60-minute piece on photosynthesis, right, I would somewhat question the reliability of it. Not that it has to be wrong, but it also doesn't have to be right. On the other hand, if your reference is a 2019 article in, you know, the ACS Journal of Biochemistry, right, it still could be wrong, right? Things get published and corrected all the time, right? But it's a peer-reviewed journal in a recent article, and so its probability of being rigorously correct is much higher than if it's something, you know, in Scientific American, right, or in the popular press, right? Not that they're trying to get it wrong, but they're not peer-reviewed, if nothing else, right? And especially things that may be controversial, right? Which source did they pick? Does that
All right.
address your concern?
Yeah. Thank you.
Yep. Other questions or problems? Right. In some sense, you know, I mean, again, everybody's in a different place. So some people did a fair amount of research up front for project one, in which case I would imagine you more easily found what you needed for project two. Some people barely had the reaction written down for project one, in which case, again, you might have to do background work on what your specific area is. And again, as I said to the biochemistry people in particular, but it's possible in other areas also, you know, beware the scope, right? I was talking to one of my colleagues who is a biochemist yesterday, and I was talking about how this scope creep, right? And he said, because, you know, somebody had mentioned they wanted to do cellular respiration, and he said, show them this diagram. I don't know if I can find it now. That had all the overlapping pathways. I mean, this one is a shorter version of it. There's one that's almost unreadable, right? These were all different biochemical pathways that all overlap, right? Do you really want to talk about all of them? Well, I mean, maybe if it's your doctoral dissertation, or if you're writing a textbook, I don't think you want to try to write up a total kinetic picture of all of these multiple overlapping biochemical processes. So you need to maybe narrow it down. I mean, this is true of photosynthetic pathways, which again tie into a lot of the cell biology of the plants. It's certainly true of things like DNA replication and cellular respiration, where it's tied into a lot of the different biochemical pathways in the cell. And so, you know, you're going to have to narrow the scope down to something that's manageable for what this is supposed to be. That also appears to be somewhat the case with the way they model combustion reactions. But other ones are more straightforward. But so the first thing to do is to really get a firm grasp on specifically what the process is, and to develop some understanding of what the language difference might be in the field, right? As I say, biochemistry, you know, the biochemical topics should really be amenable to what we're trying to do, right? Because thermodynamics and kinetics are a big issue there. Now, some of it looks a little different, right? As I said to somebody, I mean, you know, temperature dependence for some of these things is probably fairly narrowly studied, because, you know, if you're talking about a process that is fundamentally carried on in warm-blooded organisms, there's no real need to know what happens at the boiling point of water, right? That's not to say they don't ever look at the temperature dependence, right? But it's not, you know, as clear a parameter that you would vary widely as if you were looking at the Haber process, where you can do it, it's a gas phase reaction, and you could do it over many hundreds of degrees of temperature difference, right? But, you know, in general, biochemists talk a lot about kinetics, and they talk a fair bit about thermodynamics, because thermodynamics is really equilibrium, although again, that's project 3, right? But their language might be slightly different, right? They will talk about rates, right? They may not talk about orders of reaction the way we do bimolecularly, right? On the other hand, it's in there somewhere, right? Because if it's linearly dependent on glucose concentration, just to randomly pick a biomolecule, right, then it's first order in glucose, but they may not refer to it as being first order in glucose. They may call it linearly dependent on glucose concentration, right? And so you need to be a little flexible in the language and kind of learn what their preference is, right? Again, they will tend to talk about enzyme turnover or turnover rate, right, as opposed to necessarily quote unquote rate of reaction, right? Other questions, problems, anything? Since I was 2 minutes late on Monday and Wednesday, I will end 4 minutes early and balance the books for the week. Other questions or problems? Magnesium hydroxide is a strong base, yes. Sorry, I didn't see that question earlier. I wouldn't lie. I have no reason to lie. Okay, happy St. Joseph's Day.